Hello everyone, welcome to this course on finite element analysis using ANSYS Workbench. The intention behind this course is to help students, educators and researchers across the globe to complete their projects and assignments which they are working for solving any engineering problem. This session is majorly focused on geometry considerations for the finite element analysis, which means the objects in the world which we are trying to analyze for their strength, life or reliability may not have to be considered the way they are in the full form. There are opportunities wherein the geometries can be simplified and the computation time can be greatly reduced. I am coming up with 6 examples that are going to help you how to simplify the 3D geometries into the simpler form. Let us get started. Mostly we'll be dealing with the examples. The first example is the problem statement reads like this. On the right hand side, we can see a pressure vessel, which is the 3D model, and the cross section of that 3D model is going to look like a 2D cross section, which is shown on the extreme right. Validate strength of the pressure vessel due to loading. The magnitude of the pressure is 0.25 MPa. The element size to build the mathematical model or the finite element model is 10 millimeter. For the ease of the analysis, we are going to keep the weak springs on. I will let you know what about the weak springs when we solve it. For 3D model analysis, fix the top surface, and for 2D model constraint the axial movement. These are certain boundary conditions we need to consider while solution to make sure the rigid body motion behavior is not observed. I will tell you that as well. So we'll first open the ANSYS workbench. The ANSYS workbench is now open. To begin with, from the analysis systems, select static structural and pull to the project schematic. Project A has been created. We can rename that to pressure vessel 3D. The material for this 3D analysis will be kept the default material, that is structural steel. Right click on the geometry, import geometry and browse. Browse for the pressure vessel. I am going to pick small pressure vessel 3D. Open. The right tick mark indicates geometry is loaded. We directly jump into the finite element model, that is ANSYS mechanical for the analysis. Right click on the model and edit. Here we are going to learn about conducting analysis on a pressure vessel on 3D geometry. 3D geometry, when it is meshed, it is going to yield 3D elements. Further, we are going to compare the results of the 3D analysis with the 2D analysis. And we are going to appreciate the time benefit that we get when 3D model is simplified to just 2D. Computation time is of great significance. In that regard, in a given amount of time, we should be in a position to perform multiple iterations. That is only possible when we know the technique of simplifying the 3D to simple geometries. Here is the geometry. If we expand this geometry, we can see a pressure vessel solid model over here. Right click on the mesh and say here generate mesh. The examples that I am trying to solve here are not in detail. They are going to give you a very good hands-on on the commands and the process involved in solving any problem. We are going to take up the examples in detail in our further sessions. If you look at this, the geometry has been converted to a finite element model. This is the geometry how it looks like. When it is meshed, the geometry has been replaced with the small elements or the mathematical model building blocks like this. I go to selection filter over here and select the element. The moment I click on one of the element, you will come to know that for that given thickness of the pressure vessel, the element has been created and the shape of the element is going to be like this. The shape is tetra shape element. This is the 3D element. The pressure that we are going to apply for this one will be 0.25 MPa. Right click on the static structural, insert, click on the pressure. We'll double click on inside surface so that all the inside surface tangent continuity will be get selected. Once all surfaces are selected, click on apply here, and this is the details of the pressure, which means we have used a command pressure in the static structural, that is the pressure load. Under details, the magnitude of the pressure will be defined 0.25 and geometry selection already has been selected, that is 3 faces. By default it was been selected. Right click on the solution and say solve. On the right hand side we can see a message that not enough constraints are given for the model. As we discussed in our earlier sessions, on the left hand side is the status bar. It is going to show the solution status. 85% of the solving the mathematical model. The solution has failed. Now in the solution it must be observed that this red symbol indicates that there is a failure in the analysis. For that purpose, we have to come down here on the right hand side, double click on the messages. In the messages, look at the error. Double click on that error. Solver pivot warnings or errors have been encountered during solution. This generally happens because we have defined the load but the boundary condition is not yet defined. That is the reason why when we were trying to understand this problem statement, there was a note over there for 3D fix the top surface. That boundary condition will support the solution. Let us see how it works. Right click on the static structural, insert, click on fixed support. Select the top face over here, apply. Right click, solve. Mainly, we should look for deformation and the stress on this pressure vessel, and the same thing we are going to observe in the 2D analysis as well. Right click on the solution, insert deformation total. Right click, insert deformation or stress, von Mises stress. Right click, evaluate all the results. Click on total deformation, that is 0.00476, stress is 6.21. Scroll for zoom in, zoom out. This is how the behavior is going to look like. Below, click on the graph and see the animation, how it is going to expand. This is an exaggerated simulation. We can see the scaling over here. This deformation is scaled largely for the better visibility. We stop that animation, but we know the stress induced on this pressure vessel because of the application of pressure. We refine the element size. Coming back to the simulation, right click on the mesh, insert, click on Sizing for the body, from selection filter, click on this body, select this body and say apply over here. Element size should be 10. Enter. Right click on the mesh, generate the mesh. The geometry will now get updated with the new size of the element, that is 10 millimeter. This is how the finer mesh model looks like. This refined mesh is capturing the geometry more accurately than the previous mesh. Right click on the solution, solve. We consider this element size and the results pertaining to this particular element sizing. The results that we see are the deformation and the stress. .0044 is a deformation, stress is 6.11, and this is the location of the stress and this is the contour plot over here. With this, now we are moving on to conducting the 2D analysis. Before that, I click on the mesh over here, come to the statistics and see the statistics. The node count is 50,679. Let us round it to 50,600. Come back to the home page of ANSYS. Press hold static structural, move it over here beside the project A. Rename this pressure vessel 2D. Enter. Material we are not going to change the way we did it for project A. We are going to consider the same material, but click on the geometry over here, change this analysis type to 2D. By default in ANSYS mechanical the analysis type will be 3D, that will be changed to 2D. This is an important step that you have to remember. Right click on the geometry and say here import browse. Now the geometry of interest is pressure vessel 2D. Open. Geometry is not loaded. This is the right tick mark. Double click on the model. This opens the mechanical. Previous mechanical window will be closed. The geometry for the 2D pressure vessel is now loaded. We can observe that cross section over here. Click on the coordinate system. One thing we must observe very carefully, that the coordinate system that is a reference to the geometry, the y-axis is passing through the center axis of the pressure vessel and the cross section is lying in the xy plane. This is mandatory. There is no compromise on this. If this does not happen, then ANSYS will not consider this geometry for the analysis. So please make a note of this point. Right click on the mesh, insert, click on sizing, click on the body over here. This is a surface body. Click on this body, say apply in the details. The element size should be entered as 10. Right click on the mesh and say here generate the mesh. We haven't changed the geometry type for the axis symmetry. Click on geometry over here, change the 2D behavior as axis symmetry. Whenever we are analyzing the circular profiled geometries, the way we have considered the cross section for the pressure vessel, this has to be an axis symmetry model. Now you click on the mesh over here or generate the mesh over there. That should give us the axis symmetric nature of the body, but still has not changed. We'll just continue to clear generated data. We'll just clear generated data and right click on the mesh, generate the mesh. Yes, the mesh has been created on this pressure vessel cross section. Now click on the node count. Mesh, say here statistics, node count. In the earlier simulation, that is 3D, the node count was close to 50,000, but in this case it is just 346. Here one thing we must learn, higher the node count, higher is the computation time. because solution will be done for each and every node present in the finite element model. So each and every node need to be solved means that much of time is involved. But in this case, it is a very less number of node because it is a 2D geometry. Right click on the static structural, insert, click on the pressure. Line here, just double click on internal line. It is going to take the tangent continuity and select the entire inside surface line and click on apply over here. The pressure is 0.25 MPa. Results that we are interested in, right click solution, insert deformation, total deformation, right click insert stress, von Mises stress. One more thing we have to note from our problem statement, that is considering the weak springs on, and for 3D anyway we have fixed the top surface. For 2D model, constrain the axial moment. We are going to constrain the axial moment. This is to add a boundary condition to support the solution. Right click on the static structural, insert, click on the displacement constraint over here. This top edge select, the top edge need to be selected, say apply, y direction should be 0. X we can keep it free for the expansion purpose. With this load and boundary condition and the mesh size, right click on the solution, say solve. This solution should be much faster because the node count is very less. That is just approximately 300 or 400. But earlier for 3D, it was 50,000. Total deformation 0.0044 and the equivalent stress is 5.909. We will see this stress result and the deformation result with the 3D analysis that has been conducted. Come to the home page over here, open the model. We'll see the result by keeping the windows side by side. We have the results for 3D analysis and 2D analysis now. Right click on the taskbar, show desktop, maximize the mechanical window for 2D, maximize mechanical window for 3D. Windows left and click on this for right. One is 3D analysis, another one is a 2D analysis. We click on the stress value. Equivalent stress in the 3D it is 6.11 and in the 2D analysis it is 5.909. This is a very negligible difference and this can be considered. But if we look at total deformation, it is 0.00447. In this condition, it is 0.00447. The deformation in both the cases are almost matching. The takeaway here is, in your project work, in your assignment, or in your project that you are working in the organization, if at all you think that a pressure vessel need to be analyzed or any cylindrical geometry that need to be analyzed which is having a very constant cross section throughout 360-degree rotation, then this is one of the recommended approach for solving the problem. If at all there are some undulations are present on the periphery locally, cutouts are present, welds are present, ribs are present, cutouts are present, then this approach is not applicable. The logic is very simple over here. Along 360-degree axis, wherever we cut, the cross section should remain the same. If that is the case, then you can do the axis symmetry analysis. One more condition we discussed is the cross section that we take must lie on the XY plane only and Y axis being the axis of revolution. I hope you enjoyed this particular problem. We are going to move on to the next problem for the similar comparison purpose, but there the analysis approach is different. We'll come back to the home page. Right now let me close these two windows. The next problem statement reads like this. On the right hand side we can see there is one long tube and extreme right is a 2D cross section of the tube. Assume that there is one water pipeline which is running from your home to 1 kilometer distance away where there is a water source. The goal is to understand the stress distribution in the tube because of the water pressure. Let us put it in other words. We want to understand whether the tube is going to rupture or fail for the pressure or not. In that regard, the whole length of the pipe cannot be considered for the analysis. It is going to be of huge computation time for solution concerned. In that regard, only cross sections will be analyzed and the results will be compared. We are going to do that experiment here live now to appreciate the approaches of the 2D analysis against the 3D analysis. The problem statement reads like this. Evaluate the stress induced in the pipe due to pressure. The pressure is 0.25, same as the previous problem. Element size is 1 millimeter for 2D and 5 millimeter for 3D. This we are keeping just for the change between 1D and 2D. So we are going to keep the weak springs on to add kind of supports for the analysis and to support the solution. Coming back to the home page of ANSYS, press hold static structural and move it over here. Right click, rename this one and rename that to pipe 3D. Right click on the geometry and import geometry browse. Pipe 3D. Or you can say tube 3D. Keeping the material default, double click on the model. We know the pressure value 0.25. The mesh size should be, I think it is, it is 5 millimeter. The mechanical window for 3D tube is now open. We maximize that window. Maximize the window, right click on the mesh, insert sizing. Select this 3D body, apply. Element size is 5 millimeter. Pressure, right click on the static structural, insert pressure. Select the inside face, the entire face is selected, apply. The pressure is 0.25 MPa. We are not going to add any other boundary condition to this. We'll begin with adding only the weak springs. Analysis settings. Hover to the weak springs. Turn that to on. Right click on the solution. Insert deformation total. Right click, insert stress, von Mises stress. Right click, solve. It is going to convert the geometry into the mesh or the finite element model first. Pressure will be applied. Solution will be carried out. Results will be produced. Total deformation and the equivalent stress we can see over here. Equivalent stress is ranging from 4.5 to 5.194. Total deformation is 0.028 to 0.034. Let us keep it as is right now, and if possible we can try to add some boundary conditions to make the deformation uniform. Looks like there is instability in the deformation over here. Right click on the static structural, insert, click on displacement constraint. We can hover to the displacement constraint. Here is that. Face select, zoom the face, select this end face, and similarly on the other side we'll zoom that face and select that particular face. While selecting multiple faces, press hold the control. Apply. In this case, the y and x component, we are going to keep it free. Z component will be fixed because there is no elongation that is going to happen along the axis. Let us try to solve it again to see or to witness the uniform deformation happening across the length of the tube. This tube I have considered a very short length. If at all it is of, let's say, 1 kilometer long pipe, it is not practical to consider and analyze that tube. In that regard, we are going to appreciate the new modeling technique of the ANSYS workbench, that is the plane strain analysis. Look at this. This is how the behavior of the tube is going to look like. For instance, we are going to change this deformation scale just to 1:1 and animate that. This is how the stress is going to be generated in the tube by application of 0.25 pressure. The stress induced varies from 3.9 approximately 4 to 4.7. Deformation is 0.00026. Click on the mesh over here. Under the statistics, we can see around 17,776. We'll round it off to around 18,000. How this problem can be simplified to 2D and without affecting the results, we are going to demonstrate now. Coming back to the home page of ANSYS Workbench, static structural press hold and move it beside project C. Rename that and rename it to pipe 2D. Right click on the geometry, import geometry, browse. Come down, that is tube 2D, open that. Geometry is now loaded. This geometry has to be converted in the analysis type from 3D to just 2D. Double click on the model. Here we have to change the analysis type to 2D, and under 2D we are going to do the plane strain analysis. Earlier we did axis symmetry analysis, but this is going to be a plane strain analysis that we are going to set it now. This takes some time to load the geometry, some time to the mechanical, so you have to bear with me. The geometry is now loaded. We click on geometry over here, change the behavior from plane stress to plane strain. By default it will be plane stress. We change it to plane strain. Right click on the mesh, insert sizing. The sizing of this body, surface body, click on this, apply, will be just 1 millimeter. Right click on the mesh, generate the mesh. This is a 2D geometry. We can see, witness that static structural insert pressure on the inside edge, apply, pressure will be 0.25 MPa. Right click on the solution, insert deformation total. Right click, insert stress, equivalent von Mises stress. Right click on the solution, solve. The way we did for the axisymmetry analysis, the same way we are going to compare the results for this as well. In the previous case, it was having around 17,000 node count, but in this case, mesh, if we see statistics, it is just 392. A significant reduction in the node count, which means significant reduction in the computation time for this one. The solution did not happen. We are going to click on analysis settings, weak springs on. Right click on the solution and solve. To support the solution, boundary conditions are essential. We are keeping the weak springs on. We'll see whether that is going to support solution or not. Solution is completed and total deformation and stress values are out. Total deformation in this case is 0.00027 or 0.00026 and stress ranges from 4 to 4.5. In the previous analysis, if we see here, Windows left, and this window is right. Look at this. The total deformation first on the 3D 0.00027, and this deformation is in the 2D 0.00027. Deformations are absolutely matching. Equivalent stress is ranging from 4 to 4.7. Equivalent stress ranging from 4 to 4.5. No much difference. One thing we are going to learn over here, along the length, wherever we take a cross section perpendicular to the axis, don't you think the cross section will be just like a two circles? Yes. In that regard, why do we have to conduct analysis on the entire length of the pipe? We just take the cross section and analyze that. Whatever the results that we find on the cross section will be same across the length of the tube. So this is application of the plane strain analysis. In industry or in the assignment that you are trying to solve, if the geometry is of similar kind, wherein on the periphery there are no localized holes, undulations, ribs or the projections, it is completely planar. About the axis, the cross section is uniform, but you are not at all interested in the longitudinal deformation or the strain, but the boundary conditions are uniform, but you wanted to understand the stress or the deformation behaviors, then it is recommended to go for the plane strain analysis against 3D analysis. With this, we are going to move on to the next example. Let me close these two windows for instance. Coming back to the problem statement page. Problem statement 3 reads like this. There is a bracket which is 3D having certain thickness of 3.04 and loaded with a force of 500 Newton. The same geometry can be simplified to just 2D on the right hand side shown over here. Whenever you come across the geometries which are loaded only planar, means only in plane loading is there is no bending load. Or if you are very much sure that because of application of the force, the geometry or the body is going to only deform in its plane and not going to bend in z direction, then such geometries can be simplified to plane stress geometries, plane stress model. We'll take this geometry for analysis and see how it goes. Coming back to the ANSYS workbench again, press hold static structural and bring it to the window over here. Rename that to bracket 3D. Geometry, right click, import geometry, browse. We go to the bracket 3D. I'm just finding out that particular file. Coming back over here, click on bracket 2D is over here, but I don't see that bracket 3D in this case. Anyways, we'll take the bracket 2D itself, open that, double click on the geometry. We assign thickness to that as 3.04 millimeter. It is opening in the space claim. The space claim is open. Maximize the window. Let me pull this geometry from design. Say here, pull. Select this face, pull it to 3.04 millimeter. We cancel this window. Open the model, that is going to open the ANSYS mechanical, wherein we are going to convert a geometry from just geometry to finite element model. This is going to be the plane stress analysis when we do a 2D, but right now we are doing a 3D analysis. Mechanical window is open. Let me maximize the window. Right click on the mesh, generate the mesh. This convert a geometry to finite element model. Right click static structural, insert, click on the force. At the bottom face, apply. The force should be defined by the components. Components in the y direction will be minus 500. Downward force. Right click on the static structural, insert, click on the fixed support over here. At the top face, apply. Right click on the solution, insert deformation total. Right click, insert stress, von Mises stress. Solve this. Click on the deformation over here. This deformation is 0.001. Stress will be 11.795. We just animate that to see how it behaves. Right click, set. In the isometric view, we are seeing the animation. We'll make a note of these values once again. Total deformation is 0.001 and the stress is 11. Mesh. The node count in the statistics is 1543. We'll go back to the workbench window. Click on the static structural and place it over here. Right click on the static structural, rename that to bracket 2D. Right click on the geometry and say here import geometry, browse, that will be bracket 2D. Bracket plate 2D and say here open. Geometry is loaded. Since we are trying to understand a comparison between 3D and 2D analysis, this geometry analysis type has to be changed to 2D only. Now double click the model. This opens the surface body in ANSYS Mechanical. The way we are changing the 2D behavior from in the first example for pressure vessel, we changed it to axis symmetry. For second example, for the pipe 2D, we changed it to plane strain. In this case, we are going to change it to plane stress. When we rotate the body, it is a surface body. We expand the geometry over here, we can see this symbol as a surface body. Click on geometry, change the 2D behavior to plane stress. By default, it will be plane stress itself. Click on this and the thickness has to be defined as 3.04 millimeter. And right click on the mesh, generate the mesh. Earlier for 3D meshing, it was around 1500, but in this case, it is just 456. Significant reduction in the node count. When it is meshed, we can see a 3D representation of this plate, whereas the surface geometry is just 2D. Click on the display over here, thick shell and beams, switch off that. Now you can see just a surface. We keep this on so that it is not necessary that we have to have a 3D analysis itself. That can be simplified to 2D the way we are doing it over here. Right click on the static structural, insert, click on the fixed support. The edge should be fixed, top edge. Apply. Right click on the static structural, insert, click on the force. At the bottom, it has to be applied. The magnitude of the force will be with respect to the components. Y direction minus 500 Newton, enter. We can see the force application direction and the magnitude. Right click on solution, solve it over here. Once solution is complete, we are going to compare the results of 2D analysis and the 3D analysis the way we did it for previous simulations. Right click, insert deformation total. Right click, insert, click on the stress and von Mises stress. Right click on the solution, evaluate all the results. Total deformation is 0.001, stress is 12. We'll open the 3D file. Total deformation is 0.001 and equivalent stress is 11.795, which is approximately equal to 12. Windows left, animate this behavior. Click on this one. Windows right, we're going to animate this behavior as well. Click on the display. We're going to switch off this mesh, but it's not available over here since the window has been compressed, or we can do it right now here. Windows right, click on the equivalent stress and animate that. We must understand, appreciate this beauty. Left hand side is 3D analysis, right hand side is a 2D analysis. In both the cases, computation time for 3D is higher, computation time for 2D is lower, but the results are almost the same. Whenever you solve such problems wherein the geometry is planar and there is only in plane loading happening, expectations are also that deformation is going to happen in plane, then immediately those geometry should be treated as a plane stress analysis. The condition we must remember in this case is the geometry should be lying in a xy plane only, and not even a single micron of offset in the z direction is accepted. No, the geometry should be in the x positive and y positive, and it should be lying exactly in the xy plane. But in 3D, the geometry can lie anywhere. There is a huge flexibility in this case. I hope this has given a very good learning on when to use the plane stress analysis without compromising the result on the 2D analysis. We close these windows as of now and we'll move on to the next problem statement. The next problem statement is very interesting. This is a kind of an impeller. Evaluate the stress induced in the propeller due to the rotational velocity. Here I have entered the force, that is a copy paste from the previous slide. Don't worry about that. We are going to induce a rotational velocity to the blade. In this case, the goal is we are going to conduct analysis for the partial model and the full model and see what is going to be the difference in the results. I'll tab, come back to the home page of ANSYS, static structural, and pull it down over here. Right click on the static structural and say rename to propeller 3D, or I rename that to propeller full model. Right click on the geometry and import geometry, browse. We open that geometry, that is let me check which geometry is that. It is propeller, rotational velocity propeller. Open that file. Geometry is loaded. Open the model directly. We are not changing the material for any of the analysis what we are doing, because this session goal is to clarify the concepts, how the 3D analysis can be simplified to either a 2D or the case we are going to solve it now. This case is going to be a comparison between a cyclic symmetry model and the full model. The geometry has been loaded into mechanical. Maximize this and right click on the mesh, generate the mesh. This is how the finite element model is going to look like. Right click on the static structural, insert, click on the fixed support. We are going to fix the center of this rotational cylinder. Right click on the static structural, insert, click on the body load, that is rotational velocity. It is going to ask the magnitude with respect to the components. We are going to create a coordinate system over there. There is no default coordinate system at the center. Insert coordinate system at the center over here, and that should be at the center. Z-axis is the axis of the rotation. Rotational velocity, we are going to give about z-axis, the rotation, let's say around 20 radians per second. With respect to the newly defined coordinate system, the rotation symbol can be seen at the center now because this boundary load rotational velocity is referencing the newly created coordinate system. Magnitude is entered over here. Fixed support is given at the center. Don't expect that this fan is going to rotate now. We are going to capture the centrifugal effect during the rotation and understand the deformation and stress coming onto this fan body. Right click on the solution, insert deformation total. Right click on the deformation, insert stress, von Mises stress. Right click on the solution and say here solve. This may take some time to produce the results. Once the results are produced, we are going to consider the other model that is only the part of this, that is only one fan, and do the analysis without affecting the results. Total deformation we can see here, very less deformation, 1.37 e raised to minus 6. Stress is 0.005. A very small amount of stress. Let us animate that. This is how it is going to look like. The deformation has been scaled significantly higher. Stop this. Now coming back to the workbench, click on the static structural and move it over here. Right click on the geometry and say import geometry and browse. Move to the rotational velocity propeller cyclic and say here open. We are not going to change any of the analysis type here because both are 3D analysis, but the H project, which is also a 3D analysis but simplified one. I will demonstrate why it is simplified. Right click on this one, say here rename, this is propeller cyclic. Double click on the geometry. I think geometry is not required to see. We can directly go to the mechanical model. This fan has 3 wings and these are equispaced to 120 degrees or spaced 120 degrees apart. If at all you observe such a nature, maybe in a turbine or maybe in this kind of a fan or impeller, then there is no need to consider the entire 3D geometry. We can consider just a part of it, where if the same geometry is rotated again and again, it should be forming the complete geometry. This is how it is going to look like. Right now we are not interested in it. Close it. Directly open the mechanical model to conduct the analysis what we did for the 3D full model propeller or the blade. The geometry is loaded now. We'll maximize the window. Now we must click on the model, right click, insert symmetry. Come over here, symmetry. The symmetry that we are going to insert is a cyclic region. Cyclic region, it will ask for the low boundary and high boundary. We click the beginning phase, apply. We click the ending phase and say here apply. The coordinate system in this case required is a cylindrical coordinate system. For that, right click on the coordinate system, insert coordinate system. Coordinate system should be required at center of this space over here. Click apply. That should be a cylindrical coordinate system. This is how the y is now becomes a rotational axis. Now come back to the cyclic region, change this coordinate system to coordinate system that we have created right now. For instance, we can rename that for cyclic. Rename cyclic. Now for this particular boundary condition or the symmetry what we defined, the coordinate system referencing to that is cyclic. Right click on the mesh, generate the mesh over here. Click on the mesh, see the statistics, the node count is 2500 approximately, but in the previous 3D analysis, click on the mesh, the node count is approximately 3700. There is a reduction in the node count in that case. Right click on the static structural, insert, click on the fixed support, the same what we defined for the previous analysis. Right click on the static structural, insert, that is a body load. Rotational velocity will be added. Defined by the components. In the y direction, it should be with respect to the coordinate system, that is cyclic, 20 radians per second. It should not be in a y, it should be in a z direction. 20, y will make it as 0. Now we can say the rotational symbol with respect to the cyclic coordinate system. Right click on the solution, solve. Once solution is complete, we are going to see right click insert deformation, total deformation result, right click insert stress, von Mises stress result. Right click on this one and evaluate all the results. Total deformation is 1.3 e raised to minus 6, stress is 0.005. Is it not the same like the previous one? It is. Total deformation is 1.3 e raised to minus 6, stress is 0.0051. But in this case, if we want to see the full model, click on the solution over here. Number of sectors, that is the cyclic solution display, has to be 3. Now model also is going to be a complete full model. This is the representation only. Now there is no difference between the previous analysis and this analysis. We click on the solution over here. Instead of 3, we just say 1 over here. That is the actual analysis what we have conducted. What we learned in this analysis is even the 3D analysis can be simplified if at all there is a particular nature in the geometry. In this case, for 360-degree angle at 120 degree each of these blades are placed. So we can just consider only one blade if required, that can be expanded to the final model. This is how it's going to look like. And look at the pattern of the stress and the deformation. They are the same. What is the benefit we got here in doing all this analysis? The benefit is computation time. In finite element analysis, computation time is very, very important. Having the control about this computation time, trying to solve the problems faster, will help you to conduct more iterations in a given amount of time. With this, we are going to move to the last example, which is also very interesting. I hope you are following and enjoying the tutorials I am demonstrating to you. Coming back to the problem statement page. Now I think we have 2 more examples. The next problem statement reads like this. Evaluate the deflection in the tank due to water pressure. We are going to demonstrate this full model and then extract the mid surface of that and conduct the analysis. Click on the static structural, press hold, and this time we'll place it over here. Right click on this, rename that to tank 3D. Right click on the geometry and say here import geometry, browse. Tank 3D geometry will be considered now. Open the model directly in the mechanical. We apply the pressure of 0.25 the way we did it for the previous analysis, and we will see what is going to be the results. The tank 3D file is now open. Now let us answer a few of the questions. In this session, we have solved the axis symmetry analysis, that is the pressure vessel. This also is circular in nature and this also has a uniform thickness. But can we consider this as an axis symmetry problem? The answer is no, because in the axis symmetry problem, wherever we take a cross section passing through the center axis, the cross section should remain the same. But in this tank condition, the cross section along 360-degree angle will not be the same. In that regard, this cannot be simplified to axis symmetry. This is a 3D analysis. Right click on the mesh, generate the mesh. We are going to generate the mesh for direct 3D model of the tank. The goal of this analysis is conducting simulation on 3D tank, then converting this tank to a surface body and applying the load there and comparing the results and the time required to solve both the models. Right now in the status bar below over here, we can see only 5% of meshing has been done. This takes some time to generate the mesh. ANSYS has taken a good amount of time in building this mathematical model and the mesh over here. We can see that for this body, elements that are generated are 3D elements. Let me go to the element select. In the selection filter, select any one of the element over here, which means the geometry has been now replaced with these small building blocks which are called as elements. Click on the statistics over here. That is going to give around 57,000 node count, which is a very good amount of number for such kind of analysis. We are going to apply the pressure and see what will be the deformation and the stresses coming on this geometry. Right click on the static structural over here, insert, click on the pressure. To select all the inside faces, we just double click one of the inside face. It is going to take the tangent continuity till the neck of the tank. I think that is good enough. Say apply. Magnitude of the pressure is 0.25 MPa. Right click on the static structural, insert fixed support. Let us assume that the tank is placed on the ground rigidly fixed. With these two boundary conditions and the load, right click on the solution, insert deformation total, right click, insert, click on the stress, that is equivalent von Mises stress. Let me solve this problem. Right click on the solution, solve. We can see on the status bar on the left hand side how it is going to show the progress with the messages over there. 68% solving the mathematical model, 97%, 100% writing the results to the file. The solution is ready. It's very fast and the deformation is 0.41 and the stress is around 128 MPa. We can just animate that to see the behavior. The pressure application generally will not be like this. Especially for such tanks, it is going to be of the hydrostatic pressure. Right now, I am applying the load for the demonstration purpose only. Click on the result over here. The deformation scaling is magnified so much, we make it as 1:1 scale. This is how it is going to look like. Now we can animate that. Stop simulation. Now we switch to the model. But we make a note of this number, that is 57,000 node count. Coming back to the home page of the ANSYS, we are going to create one more static structural file. We move it over here. The same, right click on this one and say here rename tank 3D itself. We'll say shell elements. We can transfer the geometry from this previous file to this file by pressing hold there and pulling it to the new project. The geometry has been successfully transferred. We can see a right tick mark over here. Click on the link, click on this link and delete that. Do you want to delete it? Yes, we want to delete that. Now open this geometry in the space claim. Make sure there is no space claim window open. Double click on the geometry. This will open the space claim. Now we are going to extract just the mid surface of this entire tank. One thing we are sure about this tank is it has a uniform thickness across, because that might have been done with a complete solid model and with all the cutouts at the periphery. Then a designer must have used a shell command to make the inside surfaces hollow to obtain the uniform wall thickness for the entire body. Now under the space claim, we are going to use a very nice command under the prepare, that is mid surface. Click on the next surface. Automatically it recognizes surfaces. We just have to say done. From the 3D geometry over here, That 3D geometry will now disappear and a 2D and one more surface body is created. That surface body will be the mid surface of this entire 3D model. We cannot just take that entire surface body for the further analysis without understanding about any imperfections present in the model or not. Yes, we click outside on the screen over here. This is the surface body. Now if we just switch on this body, we can see one small line or the center line. This is the mid surface for this uniform wall thickness 3D body. We'll switch off that. The body also is suppressed. We are not going to take the 3D for the further analysis. The 3D body is suppressed and hidden. This only surface body will be taken care. Since the surface body is extracted out of the 3D body, we want to make sure there are no imperfections. We click on the repair, say here any stitches, see the message at the center over here. Keep seeing the message over here, no areas found. Gaps, see the message, no. Missing faces, there is one missing face. That is at the top face. If we click on this, then it will again convert to complete solid, not the shell. Complete solid. We don't want to do that. We want to live with this. Okay, split edges, there are no split edges. Extra edges, no extra edges. Duplicates, no duplicates. We must appreciate the beauty of space claim, that it has extracted the mid surface for the 3D body so neatly. Now it is a time to take this forward for the analysis. Double click on the model. ANSYS mechanical window is now open. We are going to generate the mesh for this one. This mesh generation should be fast enough. We must see that this is surface body. For the surface 3D bodies, when mesh is generated, ANSYS mechanical is going to create the shell mesh for that by default. We are going to understand about these elements in detail in our coming sessions. This session I don't want to disturb with all those types. The finite element model is now ready. We click on the mesh over here, maximize this window, click on the statistics. The node count over here is 48,234. Anyways, this mesh is finer than the previous mesh. Even though it is finer, the node count has significantly reduced. Let us understand the nature of this element by clicking the element select over here from selection filter and click on any one of the element. Look at this. This is the shell element. This is not a plane stress element. This is not a plane strain element. This is not axis symmetry element. Anyways, they use the plane element, but even though this looks like a 2D element, this is a shell element. We are going to talk more about that behavior, degrees of freedom in the coming sessions. So now next is right click on the static structural, insert, click on the fixed support that is at the bottom face and say apply. Right click on the static structural, insert, click on the pressure. Pressure will be applied to the inside faces by double clicking on any one of the face and say here apply. The pressure has to be applied in the negative direction, that is normal to the surface, minus 0.25. Right click on the solution, insert deformation total, right click, insert, click on the stress, that is von Mises stress, solve this problem. The way the computation time for the previous analysis was so short, likewise for this also the computation time should be very small because this is a single body and there are no contacts in this body. On the bottom left we can see that the solution status 90%, more than 90% of the solution is complete. Once the solution is complete, we monitor the deformation and the stresses happening on the body. Click on the total deformation, it is 0.56. Stress is 157. Let us see how much it was in the previous body. Total deformation is 0.4 and equivalent stress is 128. There is a little bit difference, but these differences, if they are less than 5% or 10%, they are acceptable. But one thing also we must carefully understand is whatever we are doing is not a professional approach of simulation. This is to make sure that the concept is clear. We are going to come up with more and more videos wherein we deep dive into each and every aspect of it to make sure that the simulation looks professional. With this, we have learned that for 3D analysis, the node count was around 57,000, but when we have made it to a shell mesh by extracting the mid-surface, the node count has drastically reduced. Even though the node count has drastically reduced, the results have not changed much. I hope this has given a good learning about the extraction of the mid-surface and simplification of a constant wall thickness bodies from 3D to 3D elements to just shell elements. Now with this, we'll close the windows and move on to the last example, which is very interesting, very simple and very easy to understand. The problem statement reads like this. Evaluate the deflection on the clip when it is fixed at one end and loaded at other end. This clip, which we all have come across, which we generally used for papers. This is a 3D model, a very small wire diameter, which can be converted to just 1D model. And we will see how beautiful finite element analysis software ANSYS is going to handle this problem. Element size used in both cases is just 1 mm and the downward force that we are going to apply is 5 Newton. Let us get started. Click on the static structural over here and press hold, move it to the project schematic. Rename that to clip 3D. Right click on the geometry and say here import geometry, browse. From here we click on the 3D clip, paper clip 3D, open that, double click on the model directly. That opens the model in mechanical. We can see at the left side bottom, the mechanical is opening. The mechanical window is now open. By considering the default material, generate on this, insert, click on sizing, select the body, this is the body, apply, and element size should be 1 mm. Right click on the mesh over here, generate the mesh. This paperclip 3D is now meshed with 1 mm element size. When we zoom over here, this is how it is going to look like. For ease of understanding, we click on element select from selection filter, select any one of the element, and that is how the element is going to be. It is a 3D tetra shape element. Right click on the static structural, insert, click on the fixed support. Fixed support is going to be on the face, and this face we are going to fix, for instance. Apply. Right click on the static structural, insert, click on the force. This particular face applied with a force defined by the components, that is in y direction negative by -5 Newton. Right click on the solution, insert, click on deformation total, right click and say here solve. We'll just focus on the deformation. While the problem is solving, we'll click on the mesh over here. The statistics of the mesh, it shows 4,000 nodes approximately. The total deformation is ready, 22 mm. We can animate that. This is how the behavior is going to look like. Keeping this as initial simulation, we'll move to the project schematic over here and click on static structural, press hold and move it over here. Right click on the geometry and say here import geometry, browse, paperclip 1D will be imported. Open that and double click on the model directly. In this case, the 3D geometry has been converted to just a wires, or the neutral axis of the geometry has been extracted to have a kind of a lines which forms the neutral line or the center lines of these circular cross-section 3D clip. The 1D geometry of the paper 3D clip is now loaded. We can see a line bodies over here. Now, the right click on the mesh and say here generate the mesh. Click on the display over here, thick shells and beams. One thing you must be wondering that how come only the line bodies have been recognized with accurate diameter? These lines are extracted from the beam, that is the 3D paper clip. So it has automatically recognized what is the wire diameter is going to be, which I may show you in one of the tutorials. But right now our focus is to understand whether we can simplify the 3D clip to 1D clip or not. The answer is yes. We are going to witness that by defining the fixed support over here, one of the vertex, this vertex, apply, right click, insert, say here force. The force will be applied at another end, apply, defined by components in y direction -5, enter, remaining will be 0. Right click, insert deformation total, right click, solve. The deformation in the previous case was 22 millimeter. In this case, we are going to measure it now. We click on the total deformation, problem has solved, the deformation is just 20 millimeter. This difference will be there, but now it is decision making of the analysis engineer on which result is going to be correct. It is not that whenever we solve a problem in the first iteration itself we are going to evaluate the results and consider the results. There will be some steps that we need to follow as a simulation engineers before concluding on the results that we are going to discuss in our next sessions. But if we look at the deformation pattern of both the bodies, the deformation pattern is the same, magnitude is almost the same. There will be some differences, but those differences, if they are less than 5 to 10%, they are acceptable. Right now we cannot say that this difference is accurate difference. When we try to model these clips by considering furthermore finite element analysis considerations or replicating the actual physics, then this difference 20 and 22 can still reduce. We click on the mesh over here, the statistics or the node count is just 135. In this case, the node count is 4000. Is it not? It is always better to simplify the models, which can be modeled very systematically by considering a special elements than doing a default mesh. Yes. So the overall understanding of this entire session is we have learned how the geometries can be simplified and only the cross sections or the simplified geometries can be considered for the analysis. You can be in touch with me on my phone, that is the India number 9481635839. You can WhatsApp me as well, or you can write me an email on caewwhelp@gmail.com. You also can visit the YouTube channel GRS CAD CAE. I am going to come up with more and more sessions in this entire course. Take care and bye bye.